gets a little bit tricky in the second layer, right? So in the second layer, we're training not specific labels, but should we believe the left classifier or the right classifier that feeds into this guy, right? And so the training label, the training set for this guy is, again, the same x, and then one left or right, assuming that y, the true y, is one of these four labels, right? And there's no mistake by the previous two predictions. So if y was 1, right? If y was 1, then h12 should have made the correct prediction, right? If h12 made the wrong prediction, then this example is not included in this training set, right? So if the downstream classifiers made a mistake that was relevant to getting a correct prediction path to the final prediction, then we don't include it as part of the training data. Right? We just assume worst case results. We just assume that this classifier will get it wrong because the upstream classifiers are already got it wrong. So train lower layers only using mistake-free training data. Yes.
So if you calculate the error rate of your final classifier, you just like take the ones that were mistaken by the upstream ones. It's just like you got it wrong.
No. You calculate the error rate on this data set. Yeah. So you always measure once you do the reduction, right? You're left with a bunch of binary. You're left with a bunch of binary classification tasks, right? And you're measuring your error on each of those binary classification tasks, and you say, what does that mean about error of the full thing? Right. So the binary classifier has no idea it's part of this larger process, right? It's just doing its standard thing, and it's reporting its you're supporting its error on the training set it was given, or you could also do validation. You could do all that stuff. That's what a reduction is, right? Once you do the reduction, you solve this reduced problem as if it was its own self-contained problem. After you solve it, there's some bigger process that backward reduces it to the original problem. Yes?
So what is the kind of the input structure of this training data for the second layer? Does it contain any kind of output from the first layer?
No, just it can. In this particular case, it does not, right? The x is just the same x we always have, right? And so given this x, should I believe the prediction of the left classifier or the right classifier? That's the label. You could, in principle, include the predictions of these two. And you could, in principle, augment x to include the predictions of the left and right classifiers. I don't know what that does to the theoretical analysis, but in principle, you could in practice. Is there a question? Yes.
Yeah, I think I'm confused. For the first layer, you're training only on. So H12, you're training only on inputs that are
Labels 1 or 2, yeah.
So, but when you're feeding in real, so after you train and you feed in real data, so it's only.
So it has undefined behavior according to this training set on instances where the true label is not 1 or 2.
Isn't that create a big problem?
No, and you'll see why in a couple slides. And then this process, recursively applies. So the classification problem is dependent on classifiers learned in previous layers, right? How you create this training set depends on what mistakes the previous layers classifiers made, right? So this reduction happens iteratively or adaptively, right? So recall there's two flavors of analysis, error reduction. So for one versus all, you get a guarantee. The reduction preserves the guarantee. It looks like this, which can be vacuous, right? And for regret reduction, you get the standard way of doing it. You preserve a guarantee that looks like this, which may also be vacuous. Here's the filter tree regret guarantee, right? Suppose each classifier has regret R, at most R, relative to its own training set that it was given. Then the whole process has multi-class regret and most log base 2 of k times r. So this is a much stronger or much better dependency on the number of classes than 1 versus all. Right. It's an inductive proof. You can see the details in the paper. To answer your question of why it's not a problem that this guy was only trained on labels 1 or 2, at test time, at test time, how you actually work backwards, right? First you run this tree, and you say left or right, or it doesn't. First you run this classifier, you say left or right. If it says left, you run this one. You don't run this one unless you go this way, right? You don't have to run every classifier. You only have to run a logarithmic number of classifiers, right? If there's 8 classes, you only have to run 3 classifiers, right? And so assuming you don't make a mistake here, then you go left. Assuming you don't make a mistake here, you go left. If you have not made a mistake, then the true label is 1 or 2, right? So you hit each of these. You hit each of these final classifiers, assuming you haven't made a mistake yet. If you have already made a mistake, like if the true label was 3 and you say go left, you're hosed, right? Like no matter if you predicted 1 or 2, you were going to be wrong. So there's no point even training on it, right? That's why. And by the way, this also leads to logarithmic running time rather than linear running time, right? Any questions? Yes.
So, order of the classes, it seems better.
So this is the worst case analysis. They assume you just give a randomized ordering.
The performance of the algorithm doesn't depend on.
It does in practice. This is a worst case analysis. It does matter, but you have to have prior knowledge to know, right? Right. So oftentimes these type of analyses are somehow either randomized or worst case analyses, right? Any other questions? Okay, so tonight we have a recitation on probability and statistics. So if you're not familiar with concepts like conditional independence, Bayes' rule, and stuff like that, just come to recitation tonight because next week we'll be looking at probabilistic generative models and hidden Markov models. That's it.